Just give it a minute and we'll get started. Okay, so hello everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar on lift station operation and maintenance. My name is Owen Volk from the Syracuse University Environmental Finance Center. Before we begin, we are going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it in the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information that you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have any questions or need assistance, please contact smallsystems@syr.edu. Now, for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. One of the many ways EFCN can support your community or utility is through our free funding application support. Struggling with an infrastructure funding application, falling short on project funding, not sure where to start? EFCN is here to help. Submit a request through the link in the chat to receive tailored support based on your project needs. And on that note, we can get started today. I would like to introduce our presenter, Gregory Pearson, Water and Wastewater Trainer at the Great Lakes Environmental Infrastructure Center. Welcome, Greg. I will go ahead and I will hand it over to you.
Thank you, Owen, and welcome everyone. Glad you're here today. And can you see my slides okay, Owen, and audio coming through okay?
Yep, everything looks good.
Okay, great. Well, I'm glad you're all here, and I appreciate your willingness to take this time out of your day to cover wastewater lift stations, operation and maintenance. Today, we're going to be focusing on 5 aspects. We'll spend a little bit of time on purpose. We'll spend most of our time in design factors, inspection and maintenance. We'll brush a little bit into emergency operations and safety, but most of our time is going to be spent in design, inspection, and maintenance today. In wastewater collection systems, we will have a couple things that happen. We'll have, am I still okay, Owen?
Yes, you still sound good in this.
Okay. Okay, we can have low points in the system where gravity flow won't continue, but also our wastewater collection system that flows by gravity eventually will get pretty deep because there's a slope that continues to slope downward to maintain a velocity of at least 2.5 feet per second in the collection main so that solids won't settle out in the line. And so the collection system could get unreasonably deep. And so those are 2 reasons for lift stations. In the lift station, you'll have basically it's a wet well, and you have pumps in the wet well. And then the controls that respond to level sensors such as float switches. And we're pumping out to a force main, and often we continue on with the gravity sewer at a higher elevation. At its most basic, a smaller lift station out in the collection system can be basically like a manhole with pumps in it. There's a wet well and some pumps, and often we'll use float switches for the level sensor that will go to a control panel to control the pump on and off, and then we go out through a force main. And so by installing lift stations, we're avoiding some potentially costly excavation to install gravity mains at a deeper level. And we can convey a lot of flow with a smaller pipeline. So there's some advantages, but the big disadvantage of a lift station is if it goes out, if there's a power outage or a pump outage, it can result in sanitary sewer overflows. So we need to also have emergency backup equipment and continual maintenance and evaluation to make sure these are operating properly. Also, lift stations do create some hazards for operators. There's electrical hazards, there's confined space hazards, and there's wastewater that contains bloodborne diseases and waterborne pathogens. So there's several hazards as well. In general, there's two types of lift stations: wet well, when the pumps are in the well, in the water, as in submersible pumps, and dry well, when the pumps are in a dry compartment. We'll look at a couple of variations of that. A lot of times, larger lift stations will have their pumps located in a dry well, and I'll show you a couple of designs that use that concept. This first one here, the gravity sewer is flowing into a wet well, and it flows through a bar screen to screen out larger objects that could affect the pump. And the pump is in a dry well that's just on the other side of a wall. And so the wastewater flows through a pipe in that wall and to a pump. That pump could be a vertical turbine, or it could be a submersible, or it could be a dry run submersible where the pump is cooled by water that flows through jackets. And so you can see that this dry well could be susceptible to potential flooding if there was a leak. And it would also contain a comminutor to grind up larger solids so that they don't enter into the pump and clog it. There's the pump right there, and it would be sending the flow out to the force main, either going to the treatment plant or to a higher gravity sewer. You have the electrical controls up above that, so that building there is at ground level, and the wet well and dry well is underground. And here's an example of that where you see some. This is a dry well with the pumps in it, and the flow is coming through the wall there. Another orientation could be a vertical turbine pump the motor's on top, and there's a shaft extending down to the pump. This is another orientation where you have the pump is in a wet well, but the motor is in the dry pump room. So that wet well fills up. You see there's a low water level and a high water level, and so you're not having a suction lift because the pump is at the bottom, and it's pushing the wastewater up. And your pump motor is at the top here, and you can see a check valve there that prevents water that you pumped to the force main from flowing back in to the wet well. And there's your pump bowl. There would be a shaft that extends down from the motor down to that pump bowl. It'd be pushing the wastewater up. And here's an example of that kind of a setup. You see the vertical turbine pumps. The wastewater is flowing from the wet well down below, and it's flowing out into a manifold. You can see 4 pumping units here, and you would have a control system here that would control which pump is the lead. Those would be alternated, so they all wear evenly. And also there is a automatic control valve, so that the valve is open when these pumps are pumping, but closed when other pumps are pumping, so wastewater is not pumped back down into the wet well. There's also a source of clean water being fed into the pump here to presumably, I believe, to lubricate the shaft bearings, because there's a shaft extending down from the motor down to the pump bowls. Another orientation here is a pump with a suction lift. So this is actually a centrifugal pump at the top, and it's lifting water with a suction lift here. So that's a different orientation. The wet well is at the bottom, but the pump is in a dry room. So you can see there's lots of variations of this. It's a centrifugal pump in a dry well area. It does have some advantages. This particular pump here, it's designed to handle solids and it's self-priming. But centrifugal pumps like this are probably more inefficient than the vertical turbines or submersible pumps that we were looking at. However, there's some advantages here. You see a nice access point where the pump can be opened. So if there was a clog, you could easily close that valve that's going to the pump and open that pump up. You could adjust the impeller and clean out debris if it was clogged. A different type of system here, I'm showing you lots of different variations, is a direct inline pumping system. There's actually no wet well. The collection system itself kind of becomes the wet well. The wastewater flows into the manifold to two pumps, and there's one check valve, no wet well. And these pumps will generally have a special design where the impeller can turn backwards if a clog or a block is sensed to unwind it. Typically, we'll see a lift station that just has two submersible pumps in it, and you can see the floats hanging down. The float on the upper left of your screen, actually someone has written lag on that, the lag pump. And it's hard to see, but on the lower right of your screen, someone has written lead on the other float. And so those operate when that lead pump lifts, the first pump comes on, and if it can't keep up and it gets high enough to lift that lag float, then both pumps will be running. These pumps will be alternated as lead and lag so that they will kind of have the same life expectancy. And these are designed to not only for redundancy, but to respond to a wide range of flows. So if you need to pump at 100 gallons a minute or 200 gallons a minute, maybe one pump can handle it. If there's larger flows, like in the rainy season, and you need to pump more, then both pumps will come on. You can also address a wide range of flows by having a VFD, which is a variable speed drive, and it can control the speed of a pump. So each individual pump can have a range of flow rates that it can deliver. And so some of the design factors is that we don't want the pumps to start too many times per hour. Generally, when they're designing the systems, they don't want the pumps to start more than between 6 and 10 starts per hour to prevent overheating. And also, we want to minimize the detention time in the wet well to less than 20 or 30 minutes, depending on who's designing it. And part of that is to make sure that we're not having excessive odors, and just sizing the pumping and the wet well appropriately. In a wet well, there's a concept of an active volume, and that's basically the distance between the pumps on and off. So the lower level is where you would pump down to. If you get to that level or above it, the lead pump will come on. If you get a little higher, the lead pump's not keeping up, the lag pump also comes on. And then you get to the upper level. If we go above the upper level, we'd have a high level alarm. And below that lower level, the lead pump would be off, of course, but if we were to go too low, we could interfere with the water that needs to be retained in the wet well for a submersible pump that needs to cool the pump. So we'd also have a low level alarm. In general, the float systems are probably the most common level system that you'll see. They control the pumps, and you can see they're at different heights. The lowest one would probably be low level, and the second lowest one would probably be the lead pump on, then the lag pump, and then you'd have a high water level. The advantage of float systems, you don't have to have power to the float itself for them to function. They can get coated with grease and debris and become too heavy to lift. They can malfunction. And they're just a simple switch that responds to gravity, and they're pretty affordable. And here's inside of a switch. You can see there's a little ball there that when the float is tilted, it just causes the switch to engage. And then when it falls back down to its normal position, it disconnects the switch. So it's sending that signal to a relay to cause the pump to be turned on or off. If you were to be setting floats, these are not the exact settings, but here's some ideas on how you would extend the float into the wet well. You'd have a high level alarm, and perhaps you'd have that a ways above the lag pump. If the lag pump comes on, you expect the level to go down because two pumps are pumping now. But if it goes above that, means that both pumps can't keep up, or there's a problem, that there's a pump outage, and you'd have a high level alarm somewhere above that lag pump. The lag pump would come on somewhere above the lead pump coming on. In this case, we're saying maybe 12 inches above the lead pump. So if the water continues to rise above that lead pump, we need the lag pump to come on. And then the lead pump on and off, that's the normal range of flows that we expect. And of course, we have the high and a low level alarms there. And here's a little image on the left-hand side of your screen of how the floats actually operate. They have kind of what they call a pigtail, where the part that can move is not the entire cable, but just the end of the cable. So when the water goes up, it actually tilts the float to cause that mechanical switch to engage. Another way to measure level or to monitor the level in a wet well, a lift station wet well, is a pressure transducer. So a pressure transducer has a diaphragm in it that measures the water pressure pushing against it, and it produces a 4 to 20 milliamp signal that sends instructions to the control panel to turn the pumps on or off. 4 milliamps would be the lowest level, and 20 milliamps would be the highest level that would measure. So somewhere in between there, we're operating. There's different pressure measurements transmitted in milliamps that would cause the pumps to go on or off. The little diaphragm could potentially get clogged from debris, so these might need to be cleaned once in a while, and they do require a power source to the sensor in order to work. A ultrasonic sensor, it sends a ultrasonic beam down to the surface of the water, and it measures the time of travel for the sound wave to go down to the level of the water and bounce back. And so it uses that time of travel to calculate the level in the wet well. And basically it's beaming a beam. There's a little cone shape to that beam, and you want to make sure that there's no other equipment that interferes with that cone because it could cause erroneous readings. So you have to have a clear path. A similar method is to use a radar level sensor. It works in the same way by measuring time of travel to the surface, but it sends electromagnetic energy instead of sound waves. And so its advantage is it's less affected by foaming on the surface of the water, but it also creates a 4 to 20 milliamp signal. And both the ultrasonic and the radar level sensor and the pressure transducer, they all allow continuous monitoring. These radar level sensors, they could be affected by other EM electromagnetic energy, such as a VFD nearby. So you have to be careful about that. And it does require a power source as well. We're going to go to our first poll, poll 1, and it's asking, what is an advantage of using float type level sensors?
Okay, launch the poll.
How is everyone doing out there? Am I going too fast? Am I going the right speed?
We're gonna give it another about 15 seconds. Okay, so results for the poll. 59% said that it doesn't require a power source to function. 9% said provides continuous monitoring data. 3% said not affected by grease buildup, and 29% said all of the above.
Okay, great job. Now, one of the advantages of the float is that you don't actually have to have a power source to the sensor itself. Of course, you need power in order for the pumps to operate, but all of the other level types, they actually have to have a source of power actually to the unit, to the level unit. Some other advantages of floats is they're affordable and they're pretty simple. They're just a simple mechanical switch that responds directly to the wet well level. So if the level rises, pump comes on. Where the other sensors, they need to be, they're digital data that needs to be processed. So there's a couple of different electronic activities that need to happen for those other types in order to control the pumps. The advantage of those other types that send the 4 to 20 milliamp signal, the pressure transducer and the ultrasonic and the radar, they provide continuous monitoring, but the float type sensors, they're not really providing any data. They're just turning on and off depending on the level. The whatever level system you have, it's sent to a panel where you control the pump operation. Other things that are in a panel would be the circuit breakers to the pumps, the electrical input, of course. You probably have a motor saver in there that monitors the heat of the motor to shut it down if there's a problem. The pump leads will be there. If you have a 3-phase pump, you'll have 3 leads going to each pump. You'll have relays that go from the sensors, the level sensors, to the logic circuits, basically, that operate the pumps on and off. You'll have an alternator that will alternate which pump is the lead and which pump is the lag. And you'll have alarm systems. In this particular lift pump panel, the upper right is a radio antenna. So that could transmit alarms or even continuous data to a SCADA system or to something that the operator could log in, or even receive a notification on their phone that, hey, there's a problem at this pump, there's an outage, or there's a high water level warning. And of course, there's lots of electrical connections. One of the maintenance things that can be done to panels is making sure all the connections are tight and there's no corrosion, because a poor connection can cause a variety of problems. Here's another example of more of a kind of a traditional panel, and you see the big red light on the top, and that red light lights up when there's a problem. And if the operators are making their rounds, they can see that red light and know they need to go and visit that lift station. You might also have something like an auto dialer that will call you if there's a problem. We can monitor the performance and the efficiency over time by looking at a couple different things. There's 2 main things that I'm going to talk about here. There's wire to water efficiency, and then there's a metric that we can use where we take the kilowatt hours of electrical power that's used for every 1,000 gallons of wastewater pumped. You can also use this concept for 1,000 gallons of wastewater treated. So you can use this as a way to monitor efficiency over time. I'll show you the second one first here. I'm going to show you an example. A pump was run and it pumped 60,000 gallons, and over that time it used 18.8 kilowatt hours. And so how would we calculate this kilowatt hours per 1,000 gallons? We would set it up like this: 18.8 kilowatt hours times 1,000 divided by the 60,000 gallons. So basically, by putting that 1,000 on the top, we're basically looking at units of 1,000 gallons. So 18.8 divided by 60 is basically what we're doing, because we have 60 units of 1,000 gallons. Would someone like to calculate that, 18.8 divided by 60? Or you can do the full thing, 18.8 times 1,000 divided by 60,000. Let me know if there's an answer, Owen.
Yep, no problem.
it's a good time to get your calculators out too. We're going to do a couple of problems here.
Yep, so we got 0.31, 0.3.
Okay, excellent. That's what I got as well. 0.31 kilowatt hours per 1,000 gallons. Now this number maybe doesn't really mean anything unless we use it to compare this particular pumping station to its own performance over time. Like for example, if we do this same test in 2 years from now, after the pump has had a little bit of wear, or after 10 years, we would probably expect to see a decreased efficiency, which would probably mean we are using more kilowatt hours per 1,000 gallons. Let's say, for example, in 10 years, it's using 0.51 kilowatt hours per 1,000 gallons. That would be 20.2 more for every 1,000 gallons. So we could actually calculate how much electricity and the cost of electricity, and we compare that to the cost of repairing or rehabbing the pump or replacing it. And so we could actually have some statistical data to justify our maintenance and replacement activity. So we can use this to compare the performance over time, compared to the original design values, and potential savings for replacement or repair. That's a good metric. There's some tools that we can use to evaluate performance of pumps, and I'll just give you some examples of some here. Here's a transmitting pressure gauge. You can determine the pumping head near the outlet. Here's a watt meter, a polyphase watt meter, to get really accurate measurements of electrical power consumption over time. A megameter that tests the motor winding insulation. And of course, just a simple multimeter is useful to test voltage and continuity and resistance, and also a clamp style ammeter. You can test the current draw while the pump is running. And I'll show you how some of these things are used here. Also, a meter is a handy thing to have, so you can know the flows that are coming out of a lift pump or force main, going into a force main. And normally we use magnetic meters because the wastewater doesn't come in contact with the internal workings of the meter. Instead, it just measures the atoms, water atoms that are passing through the magnetic field. There's a lot of things that you can do by taking a pump out of service and bringing it into the shop. But there are also some electrical testing types that you can do while the submersible pumps in a lift station are in place. For example, you can actually do mega ohm testing in place, and you'd have to disconnect the leads and disconnect the power. But if you have the leads disconnected, you can measure the resistance between each motor lead and ground. And ideally, you're looking for a reading of 10 mega ohms or greater, or 10 million ohms or greater. You can do resistance testing on the pump motor leads. Once again, the power is off, locked and tagged out, and you're taking the pump leads and you're measuring between the different leads, T1, T2, T2 to T3, T1 to T3. And you want to see a low reading, typically between 0.3 and 2 ohms, but it depends on the particular pump. You'll have specs for that. But in general, if you have a 0, it means you have a short, it's going to ground. And if you have a really high reading or infinite reading, it means you probably have an open circuit. There's something wrong with the connection in there. And also, if you take the average of the resistance testing and you compare the resistance of each lead to the average, they shouldn't vary by more than 5%. Amperage draw is done with the motor on. And in all these tests, you want to have make sure you have PPE and you're protected from shock, and arc flash. A high voltage panel could offer a lot of dangers, especially if you have 240, 480 volts. That's a lot of volts. But amperage draw also is a good thing to measure, and I'll go into that a little bit more in a second. Also, there's a new thing it's kind of new to me. Motor current signature analysis. You can actually look at the frequencies that are produced in a motor, and you can actually use that. The electrical frequencies can actually tell you about mechanical and electrical problems in the pump. It's one component. So here's how you would measure the amperage draw. Here's, once again, the pump is running, and you have the motor leads, and you can use this clamp type amp meter to get a reading on the amps. Looks like this one is pulling 18.6 amps here. So you measure the amperage draw of each leg if you have a 3-phase panel. Some very small lift pumps might have 1-phase power, but it's usually better to have 3-phase power to a panel, to a lift station. So you measure the amperage draw of each one, and they also should not vary more than 5% from the average. So you add all three together, divide by 3, and then compare each leg to the average and see if they're different by more than 5%. If they are, you could rotate the leads. For example, we have a yellow, green, and a red here. You could rotate the yellow to the green to the red to the yellow. You rotate them all in the same direction. If you were to just rotate 2, the motor could go backwards and you have a lot of damage. Mega ohm testing is you're measuring between the lead and ground, and you're basically measuring how good is the insulation, the winding insulation in the motor. So the mega ohm tester uses a high voltage, like 1,000 volts or more, but a very low current. And so it's measuring if electricity can get through the insulation to ground. And that image at the top is a crank type, kind of an older style mega ohm tester where you can rotate the crank to get your voltage. And you basically want it to be 10 mega ohms or greater. Here's a little chart. If you see a mega ohm reading of 10 mega ohms or more, it generally means the motor is good to continue to run. But if it's below 10 mega ohms, you have to start monitoring that motor a little bit more. There's something going on. And if you get down to 2 mega ohms, that means the motor probably needs to be replaced immediately. Because once the insulation allows arcing to ground, it's a short time until the motor is basically toast. This motor current signature analysis is, like I say, this was the thing that was new to me that I recently became aware of. MCSA would be the acronym, but they're basically looking at the frequencies of electricity that are going through the motor, and they can detect wiring problems and even mechanical problems. Here's a image here of a broken rotor bar on the bottom middle of your screen, and that corresponds to the image on the top right of your screen where you see a little spike. And they said, you know what, we think that means there's at least one broken rotor bar. And when they opened the pump up, sure enough, that's what it was. So by looking at the frequencies of electricity flowing through the pump, they were able to diagnose a mechanical problem, which is kind of amazing. And this particular link on this slide, that you can go to that to see several examples. It's also in your references sheet that I put together. That references sheet is like a little library. Some of the links are blogs, some of them are studies, and other ones are ones that you'd probably want to keep in your library. You can also detect if you have an out of round condition between the rotor and the stator, which could be due to assembly problem or a coupling problem. There's some tools that you can use too. If you have access to the pipe, for example, you can use a ultrasonic flow meter to determine the flow through a pipe, a portable ultrasonic flow meter. And a portable ultrasonic level sensor can be placed at the top of a lift station to measure changes in the level. That could be useful for doing a drawdown test, for example, to know exactly how much you pumped over in a pumping test. Vibration is a thing that we can measure to determine the condition of a pump and motor over time. In this particular image here, kind of some summarized monitoring results, they had a long-term trend of increasing vibration in a pump. Most likely that is due to a bearing that's starting to go out. And when I say vibration, we're talking about vibrations below the point which we could actually sense with our senses. These vibration sensors are sensing very slight vibrations. And here's some vibration sensors that are actually permanently installed on a turbine pump. And so you basically that you're looking at the increase in vibration over time. And also you see in that top image that there was a little spike in vibration due to some cavitation. So it can help you to diagnose pump problems and warn you of impeding bearing problems. Vibration could increase also because there's lack of lubrication, or because there's some kind of mechanical misalignment between the pump and motor. You can have handheld vibration tests where you go and you hook the equipment up and check pumps and motors periodically, or you can have something like you see in that upper right image where the vibration sensor is installed permanently and you're getting continuous readings through a 4 to 20 milliamp signal. And vibration, it also has been correlated with submersible pumps failures because it shortens the seal life. The seals in a submersible pump keep wastewater out of the pump. Once wastewater gets in to all the electrical and mechanical components of the pump motor, it's going to fail. When we talked about flow meters and pressure readings, if we have pressure and flow readings, we can deduce some things about performance. In this example here, you see that gauge is reading at 7. And so we look at the pressure that it's running at, 7 psi. And at that pressure, that head, it's producing 435 gallons a minute. So we can monitor the performance over time. But we can also do other things. We can compare the performance to the original pump curve designed by the engineers, and we can use pressure and flow to calculate wire-to-water efficiency. Remember, I said there was 2 ways that we can monitor efficiency over time. One of them was kilowatt hours per 1,000 gallons pumped, and the other one was wire-to-water efficiency. And we basically can monitor the performance of pumps over time by knowing the pressure and the flow. And we can use the pressure and the flow to actually calculate water horsepower. Water horsepower is the head or the pressure of that's imparted to the water, and the flow that's imparted to the water by the action of the motor and the pump. So this is the result of pumping. In this case, I'm giving an example here that we have a pump flow that's 400 gallons a minute, and the pumping head is 104 feet, and we obtained that from a pressure reading. The pressure reading was 45 psi, and we took 45 psi times 2.31 feet per psi. That's a conversion factor, and 45 times 2.31 is 103.95. I rounded it to 104. So back to our problem here, we're going to calculate water horsepower, and here is the calculation or the equation to calculate water horsepower. We take the flow in gallons per minute times the head in feet, and then divide it by 3,960, and that is the conversion factor to convert to horsepower. If we plug our numbers in, I'm going to ask if somebody can calculate this for us. 400 gallons a minute times 104 feet, and then divide that by 3,960. Let me know if we have a answer for that, Nolan.
We had one come in pretty well. Yeah, we have a bunch coming in 10.5.
Excellent. You guys are excellent students. Thank you for that. So 10.5 horsepower, that's water horsepower. We had to put in a little more motor horsepower because there's some inefficiencies to calculate. So the pumping head, it includes the friction losses, the pressure required to lift wastewater from the bottom of the wet well to the higher gravity system through the force main, and then whatever delivery pressure we want to be at the end of that. But we also have to overcome the frictions and energy losses in the motor and the pump. So we're going to retain this 10.5 horsepower here because the next slide we're going to do a wire to water efficiency example. We'll use this same figure here. Wire to water efficiency as water horsepower divided by motor horsepower, and we convert that to a percent. And so we know that we're going to use the water horsepower of 10.5 that we just calculated. But the motor horsepower we're given in kilowatts. We had to put in 11.2 kilowatts of power into the electrical motor that runs the pump in order to get a resulting 10.5 water horsepower. And the conversion factor, 1 horsepower is equal to 0.746 kilowatts. So to convert kilowatts to horsepower, we're going to divide the kilowatts by 0.746 kilowatt per horsepower. 11.2 kilowatts divided by 0.746, and I'll let you all calculate that, and Owen can let me know when he sees the answer come in.
Getting a lot of 15s.
Okay, excellent. And I left a little bit of decimals there. So 15 horsepower of motor horsepower. So we had to put in 15 horsepower of electrical energy in order to get 10.5 horsepower of water horsepower. Now we have the water horsepower and the motor horsepower. We can now divide the 10.5 water horsepower divided by the 15 motor horsepower, and someone can let me know what they got for that.
Between 69.95% and 70%.
Okay, you're even more accurate than I was. I just called it 70%. So so our wire to water efficiency is 70%. Now, if this was a brand new pump, this would be a figure that we could track over time to see how our pump is doing. We can think about the motor. The motor is losing some energy. It's not completely 100% efficient, and that's probably due to some bearing friction and some heat loss. And in the pump, not 100% of the water that goes through is being pushed every time by the impeller. There's some recirculation that happens, and of course we can minimize that by adjusting the impeller tolerances really tight. But there's also going to be a little bit of friction, even though the bearings are really frictionless, almost. There's still a little bit of friction that happens, and the friction between the impeller and the water as well. We can also use wire to water efficiency to look at pumping scenarios. And here we have a wire to water efficiency report. On the y-axis is the wire to water efficiency. On the x-axis is the system flow, and we're looking at the efficiency curves of different scenarios, running with just one pump versus running with two pumps here. So if we look at this first line, I'm kind of tracing a rough blue line for the just running with one pump, and then for running with two pumps, I'm tracing with a little green line here. And you see at some point, we're going to be more efficient with the two pumps. But let's look at a flow of 237, the lowest flow, 237 gallons per minute. You see there's a difference between running two pumps and running just one pump. The running two pumps, the efficiency, wire to water efficiency is only 17.1%, whereas running two pumps is significantly more efficient. It's 26.9%. And part of that is because if we have two pumps pumping that low flow, we actually are, instead of pumping 237 gallons a minute, each pump is pumping only 118.5 gallons a minute, which is below the ideal efficiency for those pumps. And you see at some point, maybe right around 1350 or so, the gallons per minute, it becomes more efficient to run two pumps for that flow. So that would give you some idea of do we run around one pump or two pumps, or when the second pump kicks in. And this all goes back to the ideal spot for a particular pump. Each pump will be designed for a certain head and a certain flow range. And so if you're below that, you're going to be inefficient. And a lot of times we're below because our inlet is restricted. We have low flow, high head, and high water velocity, which is not ideal. And then on the other end of the spectrum, we have high flow with too low a pressure, and a lot of times that is a result of having too large of an outlet piping. But when we're right in the middle, our pump matches the hydraulic characteristics of the system we're trying to pump in. Now we're going to go to poll 2 now. And you have to do a little math on this problem. And I'll read the title and I'll be quiet. A pump requires 12.2 kilowatts of electrical power to deliver 11.5 water horsepower. What is the wire to water efficiency? Can you give us about 2 minutes on this, Owen?
Yeah, that's fine. Yeah, we're gonna run on 30 seconds. Okay, so we're gonna do results now. So for results, 18% said 90%, 29% of our attendees said 84.7%, 48% of the attendees said 70.3%, and 5% said 67.1%.
Okay, all right. That's a little bit tricky. Let's look at the solution here. And I got 70.3%. And here's how I did it. I first of all converted the 12.2 kilowatt to horsepower by dividing by 0.746. And I got motor horsepower of 16.35. I left my decimals, so it would, some of my decimals, so it would look like maybe what you saw on your calculator. And then I had the information I needed to do the wire to water efficiency, 11.5 horsepower divided by 16.35 horsepower, and I got 70.3%. Let's go and talk briefly about some operational and emergency type actions that operators can take. One of the things to do if you have a float system is to test the float switches by lifting them with a long pole with a little hook at the end. And you see how the float switches operate. You should be able to verify that the pumps are starting and stopping appropriately and that the alarm systems are functioning. Also, another thing is to read the hour meters. The pumps should basically for each day and for each week and each month, over time, the hour meter reading should be within 10% of each other. If one pump is running a lot more than the other pump, it signals that there probably is a problem. One of the pumps could be clogged, or there's a motor problem, or so forth. And other metrics that you want to collect when you're out in the field is to verify is it running or stopped? How many pump cycles have there been? What is the runtime hours for each pump? The wet well level? Has there been any pump failure or high level alarms? And pump flows and the totalization of the flows. Those will be all good things to collect, so you can go back if there is an impending problem. You'd be able to look at your data and see, is there some changes in these things? Are we having more and more problems with a particular lift station. If you have discrepancies in run times, or over time the run time is changing, it could mean that you have a check valve that's partially blocked, so it can't completely close. So water is flowing back into the wet well, so you're having to pump the water twice. You could also have a pump impeller that's clogged with grease or debris, or you could have a motor problem. So those are all things that, if you look at the hours, you could diagnose that there might be something like that happening. In general, fats, rags, oils, and greases cause problems in wastewater systems in general, and particularly in lift stations. If you have problems with solids clogging, you might need to add some kind of a grinder pump in before, so it grinds up the solids before it enters. If you have a lot of fats, oils, and greases, it might be something where you have to go upstream and talk to some of your customers to make sure that they're cleaning their grease traps, and you'd have to make sure you visit your lift station and clean it more frequently. And also, if you have rags, you might be able to have some kind of a screen, or in some cases, cutter pumps can chop up rags. Rags are kind of the bane. That I don't think there's a guarantee that cutter pumps would protect you completely from rags. It's best to have some kind of way to screen. In general, submersible pumps are designed to pass a certain size of solids. Typically, a 2.5-inch sphere or larger should be able to pass in the suction outlet and out the discharge, but larger solids would cause a problem, and certain types of solids like grease could actually accumulate and clog a pump. And here's some examples of different types of grinder and cutter pump attachments that might help. And also, a larger lift station would probably have a comminutor that would grind the solids up small before they get to the pump. Here's an example of some operator innovations where they installed a perforated pipe so they can use air to break up grease on the surface, and they also have a little bar screen there to collect rags. So the rag is collected there, and they can just use a little hook device to pull them out so they don't actually get into the lift pumps. Another thing that's good is to have a pressure gauge on the force main and to monitor that over time. If you have an increasing pressure over time, it means that the force main is likely getting clogged with grease or debris. Low pressure, decreasing pressure could mean you're having a leak in the force main. And annually, you at least want to clean the wet well, spray it down, and vacuum it out. There's a jetting and a back truck they had pulled up to this lift station, and they're washing it down and cleaning all the debris out. It's a good idea to conduct a drawdown test to verify the speed or the flow rate of the pumps, and it's a good time to pull and inspect the pumps. You might have a contractor that has the specialized tools to actually inspect and repair submersible pumps. They do require some special tools, or you might have an in-house shop that can do that. But one of the things that's really critical on submersible pumps is the seals. They have to be changed once in a while. And the image on the far lower right of your screen, in this case, the operators found a mop head in the wet well that could have caused some problems with the pumps, and they found it and they hooked it and they pulled it out. A drawdown test, I mentioned it a couple times. It's just a way to determine the flow rate of the pump or of each pump. So you operate the pump on hand. You have an HOA switch, hand, off, auto. So when the pump is set to run on auto, it responds to the level sensors. On hand, it just turns on. And so you can pump the wastewater down, or you can actually add, typically they add water from like a hydrant up to a certain level, and they pump it for a certain amount of time, and then they see how much water was pumped, and they know the diameter and of the wet well and how far it's pumped down. They would use this equation, diameter squared times 0.785 times the height times 7.48. The 7.48 gallons per cubic foot is a conversion factor to get to get your volume into gallons. So then when you divide by minutes of time, you'll have gallons per minute. And you want to express the diameter and the height in feet to make this work. And so you'd pump the lift station wet well down. That would the amount that you pump it down would be the height. That's where that portable ultrasonic level sensor would come in handy. So you know the difference between the original level and the pumped down level. And then of course you would know the diameter of your wet well. And when you find out how many gallons you pumped, you divide it by the time that you pumped it in minutes, and you would get the actual gallons per minute. And you can do this to check the calibration of the mag meter, for example, if you have a magnetic meter. You can also use this to compare the pump performance over time, taking the actual divided by the rated to see what if you're losing efficiency. To respond to emergencies, to prevent sanitary sewer overflows, you want to have some kind of backup, emergency backup, and that could be a generator that either has an automatic or manual transfer switch that will provide power when there's a power outage. And you can also have a pumping unit, a bypass pumping unit, where you would have the lift station would be fitted with special piping connections to be able to connect between the pipe going down to the bottom of the wet well and to the force main that you're going to pump to. In general, safety ranges from completely eliminating the hazard by removing it, some kind of redesign. And on the lowest level, you don't do anything to change the hazard. You just make sure that workers have the PPE, or the personal protective equipment, that they need to be safe or to be protected. If you have to enter a wet well, as you can see this gentleman here, he has a harness and a hard hat, and he probably has gloves. They probably tested, we hope, they tested the atmosphere for oxygen enrichment or deficiency, the presence of explosive and toxic gases. So it's if you have to enter a wet well, there's a lot of hazards there. So when you even a dry well can be considered a confined space, and you have to check for the presence of gases. And a dry well requires at least 6 continuous air changes per hour, where a wet well requires 12 continuous air changes per hour. And you'd have some kind of a meter that would measure combustible and toxic gases and oxygen levels. And if you were to redesign to eliminate a hazard or to reduce a hazard, maybe you would change the wet well into a dry well, so it's easier for the operator to get to the pumps and make adjustments and repairs. The submersible pumps that we normally use do have a degree of safety built into them, because you can pull the pumps without having to enter normally if everything works right. A chain or a cable is used to lift. You have a winch that can lift those up, and so they slide up the guide rails, and installing them is the same way. You put them on the guide rails and slide them down to the bottom, and they make a connection basically with gravity to the piping. When you pull out a pump, you want to make sure you're not holding on to the cable, because if the chain breaks, it could pull you in. And you don't want to lift it by the electrical cable. You want to lift it by the chain or the cable that is intended to lift it. And the grate should only be open when you're removing the pump. A major source of injury is when someone tries to go in and retrieve a tool or a part that they've dropped in. So you always want to be aware of safety, and you always want to make sure you have the power disconnected when you're removing and installing pumps. Our last poll 3, asks what would it mean if the insulation resistance of a pump motor was 2 million ohms? 2 million ohms, that sounds like a lot of ohms.
Okay, the poll's running. Okay, so we're gonna get to the results. So 65% said that the motor should be replaced. 8% said the motor is okay to use, it's in fair condition. 10% said the motor is in good condition with normal wear, and 17% said the motor is in new or excellent shape.
Okay, let's look at the feedback here, and excellent job. So the 2 million ohms or 2 mega ohms is actually the point at which you would want to replace the motor. It's in poor condition. Here's that graph again that we looked at, where we want 10 mega ohms or greater ideally. And so I'm going to just mention here that you can visit us at efcnetwork.org. There's a funding guide there. You just click on your state and you can see funding sources. You can request technical assistance or sign up for other events like this. And you can also visit us at the Great Lakes Environmental Infrastructure Center at gleic.org. You can feel free to email me directly, gpearson@mtu.edu, and make sure you download your reference sheet that I provided. And I want to thank you for being a great audience today. I enjoyed spending the day with you. If you want to share something you enjoyed learning about, or if you have a question, this is the time to ask it. And if we don't get through them all, Owen will send me your questions and I will answer them by email.
Okay, so as of right now, we do have 2 questions that came in. The first question, someone was wondering, for the calculations, are they considered when it comes to, are the calculations considered for pump life in an asset management plan?
Yes, the asset management plan, you know, the best thing about an asset management plan, or the thing that is really the thing that you use, is having a way to compare the condition of different similar assets. Let's say you had 10 lift stations and you're looking at different ways to prioritize repair and replacement. So if a lift station serves a wide area, or an overflow of that lift station would cause an environmental or public health hazard, that would be one way to assess the priority. Another way to assess the priority is how much electricity you could save by repairing that. And that calculation we used, where we looked at the kilowatt hours per 1,000 gallons, that you could directly equate that to the amount of dollars being lost due to an inefficient pump. And if that was more than it would cost to replace the pump, you could use that information. And so I hope that answers your question, and I'd be happy to talk to you more about it. You can email me specifically, and there's some ways to prioritize which lift stations you should work on.
Okay, awesome. There are a couple more questions. Someone was wondering, why would one choose a wet well versus a dry well?
I think it's just the basic simple collection system type small lift stations. It's just easier. The water from the gravity system just pours into it. I think it's a simpler design. Whereas a dry well, you know, you can imagine it requires a little more cost to engineer that. You'd have to have an above ground room. You would have to have a watertight wall where the water is flowing. It's a cost benefit curve. I mean, if it's going to result in greater safety, it might be worth it. But I think it just comes down to an economic reason. It's just it's the most common, it's the easiest to construct, I believe.
There are just a couple more questions. Someone was wondering, can actual GPM obtained via drawdown test be used in lieu of actual rated GPM? If rated GPM is unknown.
Yeah, of course, yeah. Especially if you can do it when your station is new, or it's still in good condition. That would be a good thing to do. And even like say 20 years down the road, you're still using the lift station, but you want to calibrate the flow meter and make sure the flow meter is accurate. I mean, that drawdown should give you a very accurate measurement for both of those reasons.
Awesome. And then someone was wondering, I actually am not sure of this answer. Has there been a webinar that has been held on low pressure collection systems?
I'm not aware of one, but I believe you're talking about the vacuum type of collection systems. Those they have a vacuum pump that draws wastewater from individual homes and laterals. It goes to a tank, a vacuum tank, and then from there they pump it basically with like a force main. Those types of systems, the advantages are a lot smaller pipe. They can get by with a lot smaller pipe, so it saves some money. But you know, the disadvantage is you have you have to have a vacuum pump, and there's some additional engineering that has to happen for that vacuum system to work properly.
Okay, fantastic. Well, I think we can wrap up there. Just wanted to say a huge thank you to Greg for his expertise today. Following today's webinar, you're going to receive a follow-up email with the slides from today, as well as a link to the recording. We ask that you complete the webinar evaluation following this webinar, so you can let us know your thoughts on today's session, as it helps us plan for future webinars on topics that are important to you. Thank you again, and we hope to see you at future EFCN events.
Thank you, everyone. Thank you, Owen. And are they getting the reference sheet as well?
Yes, that is in the handout tab, but it will also be sent out in the follow-up.
Okay, great. Thank you, everyone. Thank you for your excellent participation today and the great questions. And if you want to know more, follow up on any of those, you're welcome to contact me by email, gpearson@mtu.edu.